Okay, so welcome guys. So in this video, I want to prove this famous theorem proved by the Turing. It's like maybe 50 or 60 years ago, I think. Okay, maybe 70 years ago. Okay, so this is the famous halting problem. Okay, so the theorem, I think everybody is familiar with halting problem is not computable or not decidable. Okay, so I want to talk about the details and talk about the proofs. Okay, so language, I just quickly remind, a language is decidable or computable if there's a Turing machine M, such that for x belongs to language, the m of x is 1. So basically, you can view as, or people like to say that the m of x accept. So basically, m of x just output true, right? If x is not in L, then m of x just output 0 or output, or just people like to say is rejected. Okay. So, yeah, that's it. So theorem is that the halting problem is not computable. Okay, so let's okay, so before we start, let's give a very important idea here. Okay, so very important idea I think during my Gödel or Turing is that right, suppose you have a Turing machine, right? So you can view a Turing machine as it's like a programming, it's like a code, right? So basically you just write a program language that's like you just write in Python or the C. You define something, and you can write while or you can write if, and then there is a variable and right. So you can view each Turing machine, right, as a, so let's say gamma is all the character you can use in your string. So you can use in your code. So for example, like when you write a code, you can use A, B, C, D. That's alphabet or A, B, C, D, or you can use common or different like right? And you can use number. But basically, all the string character you can use are finite, right? So it's like let's say many more abstractly, gamma just a finite set of character. Okay, and your code. What is your code, right? Your code TM, right? Your Turing machine or your code is just this, right? So it's the finite string composed with sigma, right? Okay, so I should say sigma is finite string, and this sigma star is all the set of finite string composed with sigma. Okay, so this is your Turing machine, right? But the idea is that from the set theory, if you know basic about set theory developed by Cantor, then the finite string composed with sigma are one to one onto the integer. So basically, when you compile this Turing machine into the computer is see this Turing machine as a like 0, 1, 0 or some bit string, right? So you can change it into integer. So actually, there's a way that you can make this one, right? This finite set of character 1 to 1 onto to an integer. So basically, all the Turing machine. So I should say the set of all the Turing machine. The set of all Turing machine are countable. Okay, I should say is countable, right? Because the set of is countable. Okay, so the idea is that given a code, right, given a Turing machine alpha, that I can write this alpha, right, to be a bit string, rep of the code, or basically a bit string as an integer rep of the code. So it's like somebody give you alpha here, and then in the right hand side you use here. You create some integer. Okay, so for every programming language, okay, so idea is that we will have already. Okay, so we want to prove that halting problem is not computable. So the task is that given a Turing machine and the input alpha, then there's a magical Turing machine MSX. Okay, so this is a Turing machine S and the input X, and if fx holds, then it output 1. So if SX loops, it output 0. So basically, there is a in imaginary machine. Like take two inputs. The first input is another Turing machine, and the input x. So input x is also a bit string, and then you check this. Okay, so the idea is that we want to prove there's no such m. Okay, so there's a okay, so the idea is that we prove by contradiction. We first assume that the m is this. Okay, and the proof is very tricky. The proof is that we can create another machine called D. Okay, D only has an input, have one input, right? So the idea is that if somebody give you a string, or give you a Turing machine, that D will first change this Turing machine into its number representation, or it's into bit string representation, and then it outputs, and then you check whether m is itself holds. If m is itself holds, then D will loops. If m is itself loops, then D will holds. And whenever D holds, whether the output is 1 or 0 doesn't matter. Okay. Or maybe I should want output 1. Okay. So this is the final important part, because you can view each programming language as an integer or as a bit string. So m itself makes sense, right? And this also makes sense, and this also makes sense. Okay, so what we have is that D of m loops if m of m holds, by definition, and the D of m holds if m of m loops, by definition. Okay, but what is DD, right? So if you take the m to D, so there's no because D is also a Turing machine, so D has its own integer representation or integer string representation, bit string representation. So D can act on D, then it becomes D. Just write m as D, so D of D loops if D of D holds, or D of D holds if D of D loops. Okay, so both do not make sense, right? Because given a machine and its inputs, then either has two conditions, two results. One is loops, one is it holds. Okay, so the contradiction proves that m does not exist. Okay, so this is a famous Halting problem. So the answer is that Halting problem is not decidable. So idea is that there's no Turing machine such that that Turing machine can solve this problem. And the most important proof idea, I think, is this. And one can also show that because the set of all Turing machines is countable, but the set of all languages are uncountable. Okay, so it tells you that most of problems cannot be solved by a computer or Turing machine. Okay, so it's somehow like the very bad negative results. Okay, in the next video, probably in the next future, we can use this same diagonalization to prove the very famous time hierarchy theorem. So I will see you guys in the next video. Be sure to subscribe to my channel. Thanks.